Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Everyone. Welcome all to today's workshop on geospatial foundation models for weather and climate. My name is Rohini. I work with the Climate and Environment Data Unit with UNICEF. I'm also a very enthusiastic person about GeoAI in general, and it's a great honor for me to introduce a new episode in GeoAI Discovery Series that combines both AI and climate. We launched the series beginning of 2022, and we discussed GeoAI applications and policies, ethics, future of GeoAI for good, and we included a lot of thematic sessions, including climate action, spatial digital twins, energy, ecology, agriculture, water, food systems, health, and much more. Current focus since the beginning of this year has been on geospatial large language models, and in the organization of hands-on workshop focused on building up practical skills in applying AI to geospatial data under the leadership of the curator of this series, Maria Bravelli. If you missed some of the episodes, don't worry, you can definitely watch the recordings of those events on YouTube or on our neural network to which you are connected right now. Without further ado, let me introduce Maria, who will moderate today's event. She is the professor of GIS at Politecnico di Milano at Geoinformatics Engineering course of study, and also member of the Schools of Doctoral Studies in Data Science and Earth Observation at Roma La Sapienza. Amongst her many activities, Maria is also the Vice President of the Commission of Geospatial Information of ISPRS. She's the member of the board of the UNGGIM Academic Network and co-chair of the United Nations Open GIS Initiative. I would like to invite Maria to introduce the workshop and also introduce our speakers for the day. Over to you, Maria.
Thank you so much.
Just to quickly jump in, sorry, Maria, we're just having a slight technical issue and it's not playing on the neural network. So just bear with me for a second and I will let you know as soon as this is fixed.
Oh, good. But shall we repeat or it's fine?
I mean, it's playing on, I would potentially repeat.
Okay, so we start since the beginning.
Yeah, I'm really sorry about this.
No,
don't worry.
Okay, let's just make sure that this is working now. Come on. This happens sometimes, not very often.
So this point, I disappeared and I leave Rohini.
Yeah, sorry, Maria. Thank you. Okay, I'm just fixing it now. Okay, it's going. It's fun. It's fine. Thanks, Rohini.
Hello, everyone. Welcome to today's workshop on geospatial foundation models for weather and climate. Good morning, good afternoon, and good evening from wherever you are joining today. My name is Rohini. I work with the Climate and Environment Data Unit at UNICEF, a GeoAI enthusiast, and it's a great honor for me to introduce a new episode in the GeoAI Discovery Series that is going to combine both AI and climate and weather. We launched this series in the beginning of 2022, and we have been discussing a lot of GeoAI applications and policies, ethics, and the future of GeoAI for good in general, including a lot of thematic sessions around climate actions, spatial digital twins, energy, ecology, agriculture, water, and health. Current focus of the series has been on geospatial large language models, and in the organization of hands-on workshops that are very practical in building up these practical skills in applying AI to geospatial data. And we have been conducting all of this under the leadership of the curator of this series, Maria Bravelli. If you missed any of the episodes, don't worry, you can watch all the recordings of these events on YouTube or on the neural network to which you are connected right now. And without further ado, let me introduce Maria, who will moderate today's event. She is a professor of GIS at the Politecnico di Milano at Geoinformatics Engineering course of study, and also the member of the Schools of Doctoral Studies in Data Science and Earth Observation at Roma La Sapienza. Amongst her many activities, Maria is also the Vice President of the Commission of Geospatial Information of ISPRS, the member of the board of UN GGIM Academic Network, as well as the co-chair of the UN OpenGIS Initiative. Over to you, Maria, to introduce the workshop as well as our speaker for today. I'm really looking forward to this event.
Thank you so much, Rohini, and welcome everyone to the event of today. So the main reason why we decided to organize this event is due to the fact that the recent advancement in AI and atmospheric physics have led to fully data-driven models that rival traditional APC-based physical simulations for weather and climate. So this tutorial will introduce Prithvi, Weather and Climate, which is a 2.3 billion parameter foundation model, which is designed specifically for weather and climate applications. So this session will cover the model's key characteristics and challenges in fine-tuning foundation models for new use cases. We are presenting also a practical case. We will demonstrate how Prithvi, weather and climate can be used for atmospheric data downscaling to enhance spatial resolution, exploring the broader potential of foundation models in addressing multiple climate and weather-related tasks with a single pre-trained model. But it's at this point a pleasure to me to introduce today's speaker, who is Dr. Johannes Schmude. Dr. Johannes is a senior research scientist and manager at the IBM's Thomas Watson's Research Center. His work currently focuses on AI foundation models for scientific data. In this context, he leads the development of the Prithvi Weather and Climate Foundation Model. And prior to this, he focused on geospatial big data, infrastructure, and analytics. He is a theoretical physicist by trade and holds a master in advanced study from the University of Cambridge and a PhD from Swansea University. Before joining IBM in 2017, he was a postdoc at the Kadley IPMU, University of Tokyo. I hope that my pronunciation is correct, Johannes, the Recognition Center for Accelerator-Based Science and the University of Oviedo. But Johannes is also joined by Romero Kinsler and Daniel Sayes, who will be assisting the participant. So without further delay, I will hand over to you, Johannes.
Thank you so much for the introductions, Maria, and thanks everybody for setting this up. And speaking of thanks, obviously thanks to my brilliant colleagues, Romeo and Daniel, who will be helping this session move along. So to let us get started, let me share my screen. And we're gonna have a mixture today of, some presentation material and some things to follow along live. Okay, and speaking of follow along, so the first thing I'd like you all to do is, you see there is a chat, there's this TerraTorch Slack channel, I think I'm gonna pause for a second here where you sort of head over there and, click through the things to sign up. So I think there's also the meeting chat, but, Slack is a bit more useful to discuss complicated things. So if you head to the TerraTorch Slack channel here, under tinycc/TerraTorch, and then join the AI for Good channel, there will be my colleagues, Romeo and Daniel, will be able to answer any questions, technical questions that might arise as we follow along. Okay. Good. So while this is happening, let's continue a bit. As you said, what we're going to discuss today is Prithvi, Weather and Climate. So this is an AI foundation model designed for weather and also climate applications that we developed, in collaboration with, people at NASA, Oak Ridge, and, various other institutions in an open science collaboration. The model was open sourced last September. And is joined essentially like a family of models here, for geospatial AI. There's the Earth observation model Prithvi. There was actually a comparable workshop, I think 1 or 2 weeks ago, that covered Prithvi. Applications like flood mapping, burn scars, above ground biomass. And then, the weather and climate model, you can obviously use it for forecasting applications, hurricane tracks, but also as other things, we're looking into like downscaling and gravity wave parameterization, etc. Okay. There's a very, very large team that worked on this, and all sorts of, roles. So let me just sort of not go through names here, but you see like the number of people involved. So obviously many thanks to everybody here. And with this, let's get started, okay? So I hope that by now, you're on the Terrator Slack channel, that this is fine. And let me still now take a step back and talk about a bit like, developments in AI and the intersection of AI and atmospheric physics, during the last 3, 4, 5 years. No? So, and with this, we're actually going to be talking about 2 revolutions today. One, which, most of you are probably very familiar with, is the story of AI foundation models. No, that we basically have, this sort of, long march here where people go from expert systems to then, machine learning systems, then, massive data and compute, basically unlocked, the deep learning revolution. But then we sort of have the rise of foundation models in the last, 4 or 5 years, basically where you have self-supervision at scale, massive data and compute. And the point is, in a foundation model, you train a largely task-agnostic model, in a task-agnostic way that then can be fine-tuned efficiently to various other downstream tasks. No? And the idea is, in an ideal case, you get obviously much superior performance for the downstream tasks, but you can also be more data efficient for tuning or more compute efficient for tuning, etc. So there's different metrics to explore and different benefits you can reap. In principle, just very naively saying, when you pre-train these things, and obviously the big successes were, in the language domain, you essentially let the model complete what's missing, missing text. Technically it's not even missing, it's typically just like the next word, no? But the point is like foundation models is sort of task agnostic pre-training, massive successes in language, also in vision, but definitely in language. And then the idea they can efficiently fine tune to other things, okay? Now, there's an entirely separate story here on the right-hand side of the screen, which some people are also very familiar with, but not as many probably, okay? So the first has nothing to do with AI, okay? This is from a paper, I think, called The Quiet Revolution of Numerical Weather Prediction, plot, which basically shows the improvements in weather forecasting skill, over several decades now. And, this has been a huge achievement, it's like an amazing, increase in accuracy and performance, which has been due to, the hard work of generations of researchers, grad students, professors, postdocs, etc., people in government organizations, but also improvements in high performance computing, okay? Traditionally, what happens is obviously, all these researchers reason about how to best, discretize and code up, the equations of atmospheric physics that govern these systems. And then, how to put those on supercomputers to simulate this, okay? And traditionally, this was really the pattern, no? You basically say, you take, the physical system, you describe it, discretize it, and then simulate it. Now, since a few years ago, suddenly people are using AI models to basically instead generate data-driven weather forecasts, okay? And this has gone to the point that, this is already like not the new slide anymore. This is from 23, for example, the European Center for Meteorology, for mid-range weather forecasting, ECMWF, is now running their own fully data-driven AI forecasting system. Okay, this is a huge change, no? Because if you say traditionally, this is like the domain of physics and hard coding, basically thinking about equations and discretizing this, and now people are willing to say, oh, let's just try like a fully data-driven system, that makes a forecast. That's like a very sort of big change in method. That's why we say 2 revolutions, no? Why people are willing to make this change, just to say why this sort of, change happens is because the speed up you harvest when you go from like this HPC system to like this data-driven system is massive, okay? I'm saying something like 1,000 to 10,000 times. This is a wide range, of course. It really depends like how you exactly count and quantize it. So I'm giving this sort of more as a ballpark number. I think you even find papers where people say like 80,000 times. Other times it's just 100 times, but it's very different when you run something like, for a few hours on like a distributed high performance computing system, or whether instead you just run something, for like a few minutes on a GPU. That's not what we're talking about, no? Let me also say that I'm not like claiming that, all of like weather in the future is going to be AI. I think it's really important to keep this in mind. Just because there is like new additional methods doesn't mean that there's anything wrong with old methods, It's really important to keep in mind going forward that you have like another tool now, okay? And since this has been adopted by, domain scientists, it's not, an AI story, it's really been adopted by domain scientists, as this example you showed, I can tell that going forward, both HPC, AI, and hybrid approaches are part of the toolbox, and there's really interesting developments happening in this space. Let me also say that like the vast majority of this revolution, okay, in this atmospheric science physics community, is actually been focusing on forecasting, which is perfectly sensible because this is, probably the most important problem there. But it's also important to say, like, sometimes people like say, oh, this is the same as foundation models. And it's not exactly quite the same because, in many cases, these models are like fairly large, depends what you call large for an AI model, but the people train on like, 20, 30, 40, 50 GPUs, for like 1 or 2 weeks. So this is already like a sizable compute budget, not that of language models, not even close, but still sizable. But then in many cases, this is essentially like a regression task and people sort of say, you generate a forecast, no? So not in all cases, but saying in many cases. I'm not trying to say it's sort of, that's why we said forecast emulators, foundation models, etc. Okay. So what we were interested to sort of really think about is, when we started this project is how do these things really combine? We're not the only ones out there, but I see it's much less people who like, look at this problem this way to say like, how can you address multiple use cases? And at the same time, leverage this point that you see AI can efficiently emulate physical processes, okay? Let me also say one thing sort of interesting to keep at the back of your mind is like this thing of recovery of missing information. I'm not going to say too much about this, but when you think like, actually in some sense, like weather data has naturally missing information, no? I mean, we're going to talk a lot about like nice weather maps today where everything is like dense and complete and perfect and very pristine in a setup. But in its natural state, you think like, well, meteorological data is like what you have is what you observe, no? It's like weather stations. It's what you measure with a weather balloon, what a satellite sees from space, So the measurements you take are actually sparse. You have lots of missing information, no? There isn't many measurements over the Pacific. There isn't many measurements, in certain parts of the world where there's less weather stations. There is not measurements, at every location, every single time. So actually, in principle, the meteorological problem is also a missing information problem, which is interesting because the original work done in this space of AI for weather always assumed dense data. That's changing now. There's lots of nice papers emerging, starting to look into observations, and sparsity and, actual sparse data. But the original work was really saying, assuming we have already like, perfect global knowledge of temperature, pressure, etc., how does this evolve into the future? All right. And this is how the pattern that emerged now. By now, this is sort of well established. There's a whole bunch of publications out there. Basically, what happens is you take gridded, dense weather data, typically from what's called a reanalysis data set. Okay. It's very specific data sets, but these basically have like, lots of different parameters. So you have global weather, temperature, pressure, humidity, vertical, latitude, longitude at a certain time t. You pump this through a model and you get, basically prediction for the next time step. Okay, and this is really what people train a lot in the sort of domain. Okay, and then if you apply this thing like several times, that's what people then call the auto-regressive rollout. You can go far out into the future. Okay, so typically the time step here is locked. The prototypical thing is really you take ERA5 data. Either you coarse grain into 1.4 degrees if you're, sort of worried about resolution in a transformer, or you do it like at a quarter degree, which is the native resolution of this data. You go 6 hours into the future. Data is hourly, but most people work in a 6-hourly time step. And then, people make like 10-day ahead, 7-day ahead predictions, etc. Okay. And that's why I said earlier, this has been like a massive revolution and a huge achievement. At the same time, also, this is not quite the same as the foundation model paradigm. Okay. Then here, as we say, like, for what we sort of start discussing today, okay, let me actually start going to the demo parts a bit. So I assume you can still see my screen. So here, there's a bunch of assets we have in open source about the Prithvi weather and climate model now, okay? First of all, there is Hugging Face, okay, where you see this is in the IBM NASA geospatial model family, okay? If you look through this model family, there's right now 2 models here. There is what we discussed today, the weather and climate model. And then there's here the Earth observation model, okay? And it's actually worth pointing out, if you look very closely, there's actually 2 flavors of the weather and climate model here, okay? You see exactly why. One is called, Prithvi Weather and Climate version 1.0, 2.3 billion. Another one, Prithvi Weather and Climate 1.0, 2.3 billion rollout, okay? Since I said something earlier about, rollout tuning and what these things do, you can sort of guess, there is a difference between these two. Let me also, so it's actually worth to point out, if you look at these in some detail here, There's some description here. This is all nice, but if you look at the files and versions, let me really call this out. There is actually test data for you here. Okay, so you see and it's the same data. We only put this with a regular model now. So there is actually some data for the mirror reanalysis, here. And quite important, actually, the model uses what's called a climatology, which is basically historical averages. And you find the entire climatology here as well, okay? Sometimes people, didn't find this and ask where this is because it seems like somewhat hidden. But you see basically if you're in the, repo for the base version of the model, under files and versions, you find both 1 year of data and you find a climatology, okay? I think obviously if you need more than this data, you can go to the raw mirror data. It needs like an epsilon of pre-processing. We'll get to this in a second, but I think by end of next week also we should have pre-processing scripts in the public repo. Okay. And as I said, if you look at the second version of the model, the rollout version, it's a similar story, files and versions. You see here's this version of the model as well, but in this repo you don't have the data files, okay, simply because there's no reason to clone those files twice. Okay. So what we have is one thing is we have Hugging Face, with the main collection for the IBM NASA model family. Then you have here the 2 versions of Prithvi, weather, and climate. Then obviously you have Git. Okay. On Git, we have now the actual code for the model. There's not only the code for the model, you see there's actually here some getting started guides. Okay. Pretty lean, but essentially we go over this in a second. You can clone the repo, you install, and then we added actually a validation script. So this is kind of interesting. What we found is like, it's nice to, when you install this to make sure everything runs correctly, So if you run this script, essentially there's a very pedestrian weather forecast for a few hours ahead. And it compares the numbers then you get on your local system with what we got on the reference system. And it gives you like a printout. We'll go over this at the end, but this is how to know that, hey, everything sort of like looks good, okay? Reason for this is we had some issues where people didn't reproduce like the right numbers on different systems due to various reasons, and now sort of a way to say, hey, do I actually see what the guys who developed this see? Okay, here's one way to look at this way. And then there's some example notebooks. And eventually, in the next 20 minutes, we'll go over all these things in some detail, okay? The other thing to call out though is there is a second repo we're talking about, We have an application here for downscaling, okay, which is what we discussed, how to increase resolution of, meteorological data. And this is in this repo granite, weather, and climate, but actually the better way to get this is via TerraTorch, okay? And I'll tell you in a sec later also what this is, okay? So these are the things you can find in public. Now, if we make this interactive, you head to your workbenches now, let me say one thing. There's the first thing to do is we have unfortunately a bit not quite the same type of GPU for everybody, okay? There are some issues to really make this available. So what you can follow along depends a little bit on what GPU you were to get, okay? We did this hopefully like in a lucky draw sort of way, okay? But so the first thing you might want to do where you log into a notebook is just check what GPU you have via NVIDIA SMI simply, The main thing to ask is not the specific GPU, is actually to check the GPU memory, okay? So if you, to follow everything along that I do, you will need 30 gig, okay? 32 gig or something like this. If you have less than 30 gig, okay, a bunch of things was going to run out of GPU memory, except for the downscaling, okay? So you can still follow a bit along and play a bit around, but don't be surprised. You're going to get lots of out of memory issues, except for the downscaling part, okay? That's unfortunate. We were not able to get enough GPUs with this memory, requirements in time. Apologies to those, who are now unlucky here, okay? But okay, whatever you have. So the first thing to do is, then once you're here, we're going to start working with the base model. So let me check what directory I'm in. Yeah. So you see here, the first thing is you want to clone the repo. You see, I've done this already, but effectively, let me leave the command here, git clone, and basically you clone the public repo. Once you've done this, you go into the public repo, you enter the directory, and then you would install what is there, okay? Some comments here. I'm installing this as an update and also editable. Probably editable wouldn't be necessary. The reason I'm doing this is because we're going to use the same environment for the core model and for the downscaling application. They have slightly different, requirements. So that's why I'm making this updatable. So we sort of, because we're going to change the environment basically dynamically halfway through this presentation. The next thing is the example part is optional, but we're going to run the examples and it's actually minimal overhead essentially as a Jupyter notebook, okay? Then you see here in this case, we've done this already. And now the first thing we can do, as I said, and there is this validation code, okay? So you see here, there's a command, again, Python -m validation.validate Prithvi weather and climate, and then C for a config file validation config.yaml. No, so I'm going to run this now. This is actually going to run quite a while. No, the reason why it runs quite a while. Well, let me kick this off, and then we can talk about this a bit. Okay. So again, what this does is it grabs some data, which is nice. So in this case, I had the data cached. That makes it a bit faster, but it's going to take, it's going to grab basically relevant data and assets from Hugging Face. But then you see it creates a data set. Okay, and you see the data set is actually minimal. It's just like one batch in there. It's one sample. It's a very specific sample. We just basically, this is the validation sample we use. So this is basically, specific timestamp, January 1st, 2020. So what the model is going to do now is it's going to use this to make a forecast. Okay, and again, with this model, we were looking beyond just weather forecasting. We were really interested in use cases beyond this. But since many people sort of, always ask the first question like, oh, what's the weather forecast? No, for this model, we figured as a validation, as a point of reference, let's just create a forecast. Okay, so this is going to create like a 120-hour, 5-day ahead weather forecast, and it's going to do this in the most pedestrian way possible. Okay, that's why it's actually somewhat slow. Okay, so right now it imports the model. The model is somewhat large, it's 2.3 billion parameters, so it takes a while just to load to GPU. But then also, when it does the forecast, to be a bit technical, it's going to do this with float 32, just on a single GPU. Okay, and this is going to be slow. Okay, if you want to speed this up, you could in principle, hack the code a bit, not right now, but I say it offline, wrap like an autocast to be float 16 around this. It's going to be like a massive speed up. During training at the scale, obviously we use like FSDP and bfloat 16, which also has certain speed ups, no? But again, the reason why we kept this at float 32 and slow in this validation script, so to make sure this is sort of like the most pedestrian way to run this model, such that, once you do this, you can see, hey, this checks out, okay, and I have something and I'm happy. I don't have this question, do I see the same thing that the developers were seeing, okay? And with this, while this runs, let's go back to our PowerPoint here, okay, and talk a bit about this more. So we looked at, the various open source assets here, okay? We looked at Hugging Face, we looked at the Git repo. We went also and started off our code. Okay, we said here, just to repeat this, we cloned the repo, git cloned the repo, went to the repo directory, we installed the pip requirements, and we actually now exited the validation script. Let me sort of count to 10 if you want to take a screenshot of this to write down the commands. I think we have the mods in the Slack channel, but just in case, okay, let me pause for a second here. Good. And now I'm going to show you some screenshots what basically going to happen in the validation script, okay? So I said this already here, this validation script kicks off, it creates a data set, creates the model, starts the validation run. And you see this is going to run something like, depends really 3, 4, 5, should be 7 minutes, should be like 4, 5, 6 minutes, okay? It generates a 5-day forecast, and then it generates a report at the end, okay? And as I said, you can speed this up if you want to by hacking the code a bit, but effectively you get something like this. You see like, all right, for this particular date, so this is not average forecast performance, for this particular date, for this particular run, we say, hey, this is the 2-meter temperature forecast, which you're getting on your system. This is a reference forecast where we cache the numbers somewhere, okay? Same for wind speed. This is what you just generated right now. This is what we see in reference, okay? We pick temperature and wind speed simply because they're very interpretable. This is something you have an intuitive idea, hey, temperature in, Kelvin or Celsius for this error, wind speed in meters per second. You can look at these. There's many more variables in the model, but we figured, these two are sort of nice to think about. And then when you run this, you see here, you get a relative sort of, performance. This is not a percent. This is just normalized 0 to 1. Okay. Negative means your local system did better. Positive means obviously it is slightly worse. You see here basically now, if you know about this, Porsche is not exactly reproducible, no? So you don't get deterministic reproducibility. That's why we sort of did it this way, Actually, if you run multiple times, you might actually even see fluctuations there. If you run in different systems, you definitely see fluctuations in this. Okay, that's why you're not going to get the same numbers here. In principle, not even like from run to the next in the same system. Definitely not on different systems. That's why what the code now does, it says here like validation result, okay, it compares the inputs deterministically. It really checks exactly that the model inputs were the same. So nothing broke down in the data pipeline and the data downloading. But then for the outputs, it basically says, hey, is this within 5%? Okay. Or at least, no, let's say differently. So not 5, sorry. Is that not more than 0.5% worse? Okay, it can be much better as it wants to be, but it shouldn't be more than 0.5% worse than the reference numbers. Otherwise, this thing's going to give you a false here, okay? And I think this comparison is also across more variables than these, okay? I think this is over everything we have, okay? Not just those two variables. And then you see like here actually also like as another point of comparison, the overall loss, you know, how our basic training scripts would see this. Again, doesn't mean that much, but you would like to have like sort of a ballpark number actually are lower than the reference number, okay? Say again, you know, you see basically here, when you see this validation script, ideally you want to see true to true, then you're sort of, you know, groovy. If you want to look in detail, you can look at these relative performances, you know, and see a bit, you know, how things do. Also, the other sort of thing you can look at is this validation loss, okay? All right, let's check quickly on my script, what's happening here. Yeah, you see now this is running and it's going to cook along here. It's going to run for another minute. We can just leave this cooking, you know, this is almost like running a cooking class here. And keep a bit talking and make use of the time, okay? So while this is running, let me actually tell you about the model, you know, because I told you about the background, you know, I told you about like how to run something, you know, which hopefully is happening now. But I haven't really told you about the model. And obviously, sorry, this validation run, by the way, is one of the things that's going to run out of memory. Okay, this is one of the memory hogs we're discussing today. So this is going to run out of memory probably for you. So if you were running along, you probably got to this line here, starting validation run, and then you got an out of memory error, which is totally expected if you're not at 30 gig plus GPU memory. Okay, just to say this very explicitly. All right, so then let's get back here and continue with the main storyline. So let me take a step back before talking about the model in detail, because it's really interesting when you talk about atmospheric physics and foundation models, you say, hey, the model should be able to do this and should be able to do this and this and this and should be do everything because foundation models can do everything, you know? And if you're a physicist, you're going to say, no, this doesn't sound like a good idea, you know? Because simply, you know, you're not going to have like, I mean, it would be nice, but you're not going to have one metal model that goes from like turbulence scales to climate scales. It would be like lunacy, okay? There's like a great aim to have in like somewhere the faraway future, but not today, okay? So the first thing you sort of want to do is like, when you start building like something like this, you want to say, hey, what are all the things we're not going to do? And the nice thing is, you know, about physics is that things sort of arrange themselves in scales. So you can sort of say, hey, you would like something that's useful across multiple scales. You're not just like a single scale thing, because then it doesn't seem so much like a foundation model. But in principle, you want to have something that has like sort of multiple scales. And we sort of, you know, the data we're using is ERA5 data. ERA5 data has a half a degree resolution. We're saying, you know, we would like to go from half degree resolution. It's much towards, you know, the low bottom left as we can. That was sort of the original ambition, you know? And we did this, we pre-trained on one data set, you know, and then fine-tuned on other data sets. That's basically what we're testing out. Can we pre-train on mirror, you know, and then fine-tune for higher resolution? But technically speaking, you obviously what you might want to do in this game is like pre-train and directly multiple resolutions, you know? So to teach the model about these things. But again, within reason. So the first thing to say is you want to say, what are we not going to do? Okay, then once you sort of have this, we thought about some applications, you know. I'm not going to go into all of these today, but sort of use case we're addressing here, you know. So again, we downscaled weather and climate model data. So downscaling, again, you know, for those not familiar, is what you would call an AI super resolution. You know, it's a resolution increase, okay? Terminology is a bit confusing because down, up, etc. But effectively means you have coarse resolution data. Can you make it fine? I'm going to tell you a lot about this, you know, towards the end of this presentation. You know, we looked a bit into predicting hurricanes. There is a postdoc, you know, who worked at a very nice project on gravity wave parameterization. Let me not get in what this is, but effectively it's the question about how climate models that have a certain coarse resolution only, you know, can better understand what happens below the grid scale. You know, because obviously these models have to be coarse for compute reasons. So you have to sort of still cover what happens, you know, below, for effects that happen below pixel size. And obviously we looked into weather forecasting as well. Okay, that's sort of a given. What data did we use? Okay, so we use data from what's called the MERA-2 reanalysis. You know, this is a data set, you know, created by NASA. Again, reanalysis basically means it's a blending of observation and physics that gives like a best guess of what the atmosphere looks like. Okay, so you take the observations you have, but obviously you don't observe everywhere. You then use like physics to sort of basically, you know, make sort of this best guess between observations you have and how systems should evolve, what everything should be to basically fill in the gaps in a way, okay? And we used 40 years of 3-hourly data for this, okay? Obviously, that's not what you find, you know, in what I just showed. We just put 1 year of this online, but obviously you can get everything from NASA, you know, from the actual source, no? We used 320 input parameters. Let me tell you how this comes about. Okay, so how is the data structured? You have latitude and longitude, but you have also like a vertical dimension. That's called here the level. Okay. Typically in these models, like vertical dimension is not really measured in like meters or feet or something, sometimes it's measured in pressure. Here it's measured in sort of like something called the level. It's a hybrid coordinate. Just think about it. There's like a vertical dimension, as you would expect, we call level. And then you have like on this vertical level, you have vertical variables. Cloud cover at each vertical level. That's actually somewhat special. Not many models use clouds. You have also the level height. You have vertical wind. U and V are horizontal wind speeds. Then you have pressure, and you have basically humidities, okay, of vapor, liquid, and ice, the concentrations, okay? Then, so these are, 10 parameters, no? And you have these at 14 different levels. So this is 140 parameters. But then you also have these surface parameters here, okay? So you see there's many more, and surface is sort of a bit of a misnomer. Some of these are surfaces like, or not a misnomer, sorry, it's not the right word, but it's not just like on the bottom. So you see like some is like 2 meter temperature, fine, this is temperature 2 meters above ground, 10 meter wind speed, but some of these are vertical integrals, okay? So TQV is like vertically integrated vapor, okay? So there's a lot of these things in, and obviously, if you want to look what all these things are, you can look at the Mera 2 data documentation where you see descriptions for these, okay? One commonly asked question is like, when I use the model, do I need all of these? And the answer is no, but it helps, okay? So I said, we tuned the model to different data sets, and then you don't have all of these, okay? And in principle, if you tune, you can compensate, no? The question obviously is the more you go away from the data the model was used to, the more you have to tune. That's sort of the story. Actually, the moment you change this data, you have to change the embedding to the model, retrain the embedding layers. Obviously, the further you change it, the more you should change inside the model. No, initially you might get away with like, everything frozen, just change the embeddings. Eventually, you have to gonna do at least like low rank tuning or tune a few layers. Eventually, you have to tune everything, but there's no single answer. But you'll see in some of the examples we did go away from this parameter set because we do go away from this particular data. Okay. And then data preprocessing, okay, there is diagnostic variables, they're being not available at hourly intervals. They're basically filled in by averaging 60 minutes, 30 minutes before and after. If you go to the data and Hugging phase, this is all already done. Again, we're gonna put up the relevant preprocessing script, I think end of next week, okay, middle of next week, just on Git. But obviously, the other thing you can do is you can just basically, if you wanted to cook your own data preprocessing, you can take the reference files from Hugging Face and reconstruct this yourself with this description here, and you should basically get the same thing, So how is the model itself then pre-trained? So you saw earlier, I showed you this pattern about like, how models sort of just like typically go ahead and do like the next time step now. And here again, we are, for various reasons, we want to do something a bit different, okay? One of the reasons is, again, we were interested, obviously we realized forecasting is important, but we were really interested in use cases beyond forecasting, okay? And this means, we're interested in this, like, what if the next time step is actually not in the future? Okay, what if the output is not in the future? What does this even mean? Now, is this like a useful thing to consider or not? So another thing to consider is, well, if I change the data set, what if the data is not available like at 3-hour intervals? What if it's only 6-hourly intervals? What's only like 24 hours apart? So can I make this? Do I have to like bake these biases into the model? So what we do then is the following. The model takes 2 timestamps as input. 2, because really, if you think about, the PDE behind this as drives this, really 2 makes a lot of sense. Also 2 is like what virtually everybody gets for best results, okay? So I don't think it makes sense to make more. Less than 2, you get degradation in results. But then we actually, at training time, we randomize how many of these are apart. 3, 6, 9, 12 hours apart, And obviously the model has a signal that tells it about the, the input delta. Also note that the data is masked, okay, or at least can be masked, meaning we actually remove half the data, okay? And then the output is complete, dense, okay, not masked, but it's, 0, 6, 12, or 24 hours ahead in a single shot, okay? No all this autoregressive stuff at this stage, that comes later, okay? And you see, like, one of the reasons is why the masking, there's a bunch of reasons, but one is, like, 0 hours ahead makes no sense without masking, like input equals output, it's absolutely meaningless. So one of the reasons is, there's other reasons also for this is, but if you sort of think about masking, you say like, hey, this actually like suddenly you can unlock like 0 hours ahead as a use case, no? Or 0 hours ahead, not a use case, sorry. 0 hours ahead pre-training. As I said, sort of like, because conceptually speaking, as I said earlier, like meteorological data is kind of sparse. It's kind of a natural thing, you know. In principle, if you think about, there's use cases here. If you start actually from measurement, you know, and not from reanalysis, you want to start with sparse data and missing data anyways and densify it. So why not actually bake this into your foundation model if your foundation model really should do like all these different things, you know? Then also, you know, masking is an absolute standard in computer vision. So it's nice to explore why not use this for physical data. And then finally, there's a nice thing just to say this. It's not the biggest thing here, but it actually helps you a bit with like GPU memory pressure at training time, okay? So if you basically don't use then any sort of tokens to like, you know, indicate what's missing, but just like don't have the data in there, and the transformer can do this. So transformer architecture is perfectly fine when data is not there. If you don't have the data in memory, the data is not in memory, no? So this actually helps you memory pressure. It's by far not the biggest thing. Let me say this, when we pre-train this thing, the biggest things are like going to bfloat 16 and FSTP, you know, like sharding. But you know, it adds a little bit to memory pressure. No, it helps you like a bit reduce things. All right. So, and then let me say this in a high level point of view, you know, we pre-train with this task, and then you fine-tune the model to different tasks, okay? Technically speaking, you'll see here the way this is written here, we basically say we keep the encoder and fine-tune the decoder. It's actually a bit more complicated. You see this in the downscaling story. It's more complicated because, you know, in naive sort of foundation model of things, you just like, you know, do a different segmentation problem. We're doing more complicated things here in segmentation, you know? That's why it's a bit more than this, but conceptually speaking, you keep large pre-trained parts of the model and you like, you know, tune separate other parts. For forecasting, for example, already you'll see this explicitly. We then did the thing, you know, to optimize for forecasting, where we locked everything in. Actually, let me show this on the next slide. This is probably better to say this. No, let me say this here. For forecasting, we locked everything, you know, to like 6 hours ahead, 6 hour input delta, 6 hour output delta, no masking anymore. Everything becomes dense, okay? And then you just like do the forecast into the future. That's basically where this rollout model comes from, why there's two versions. So one model was pre-trained with this masking, and the second version of the model then basically locks in only for forecasting dense data, 6 hours, etc., and does the rollout tuning. Few things about the pre-training objective. It's actually kind of interesting as well. So if you look at the naive objective, what you typically would do is, you know, no, not typically, but naive thing is you say, hey, I said there's 2 timestamps input. You know, you scale these as you would, you know, some input scaling, mean and sigma, you know. You run through a model, and then you say, all right, I'm getting to the next timestamp that is also scaled. This is fine, you know, you can do this. The negative is like you have lots of stuff you have to learn that is sort of always trivial, you know, like you have to basically say, hey, I know that persistence is a really good forecast, you know, I know that it's like typically colder, you know, at the South Pole than, you know, in France, you know, like these are like biases that are known, but now the model has to like learn everything from scratch. It also has to learn that, you know, temperature has a different scale or different parameters than wind, etc. So one thing you see very commonly people do is instead of like generating the entire like, you know, physical field, is they generate the delta from present. This is basically what you call tendencies, or you can also call it the delta. You could call it like the delta from persistence. Now persistence is like, I assume the forecast is the same as right now, nothing changes. So by basically predicting the delta from right now, I predict, you know, what the change on persistence is, or predict the tendency. And this means, you know, this model, if this model predicts 0, you already get the performance of persistence for free. So this actually works really well, you know. The problem is this breaks down when you go on 0 hours ahead, because for 0 hours ahead, this is going to be 0 on the left-hand side, like you're predicting 0. It's kind of boring, no? So what we said is like, look, how can we pre-train the model such that, you know, we don't like, you know, just do the naive objective, but that actually we get some free information, no? And that like also 0 lead times make sense. And we said, look, let's use climatology, no? So basically what the model predicts is then it predicts the difference from climatology, so from historical climate, okay, from historical average conditions. And then it's also normalized by basically the variance, or, you know, the standard deviation, sorry, here, of historical climate. Okay, and then the model we give it also climatology as input. So the full thing is, you know, you see now inputs to inputs with these randomized input deltas, the J here. We give it the climatology as input because why not? You know, and then the model basically has to generate what's the deviation from expected climate as a target. Okay, again with different set of randomized lead times. Okay, it's the pre-training story. So for the architecture itself, okay, I'm keen to keep this somewhat lightweight, but we said like masking is quite key. You know, at the same time, that means you can use a vision transformer. At the same time, you have to say, look, actually we're doing this, you know, this is like half-degree resolution. So this is like something like 360 by 576 pixel, not a crazy amount actually, you know. But typically people in weather and climate models like to use really small token sizes. So we use like a 2x2 token size. Suddenly you have quite a few tokens, okay? Basically 180 by whatever, 288, okay? So typical, like, just like vanilla vision transformer doesn't quite cut it. So what we do here is we basically use like sort of a windowed attention mechanism, where there is windowed regions and attention basically either runs locally or region to region. And then we can also mask in two different ways. We can mask just like we mask out individual tokens, and we can mask out like individual windows. And we actually do both. Okay, we alternate both. Roughly speaking, the idea is, if there's a motivation, masking locally is almost a bit like, missing observations, almost, definitely not the same, okay? Masking globally makes the model comfortable, like, with running with large areas missing. And there's cases where we run the model for that downscaling application in the box, where it is not the global context anymore, So in principle, you get somewhat reasonable zero-shot results if you run the model just in the box, because it was like trained with like global masking, it's comfortable with this. That's sort of something to say, and we found reasonable performance with these two things. One thing you can do, let me say this quickly, is you can, and this is in the code, So when data becomes dense, when there is no more masking and everything is rectangular and nice, you can add sort of like a Swin-like shift to this. There's something like an option in the model called decoder shift, encoder shift. I'll tell you in a second, show this again, and you can turn this on or off, okay? Then, as I said, here there's two sort of types of the models. I said you in Hugging Face already. There's the base model, 2.3 billion parameters, 2 inputs, trained with 50% masking, initialized from scratch. Okay, we use this for downscaling, for the gravity wave case, etc. And then there's the rollout model, where, as I said, we locked everything in. We keep the inputs like exactly 6 hours apart. We keep the output exactly 6 hours ahead. Then you can go with rollout, multiple steps to the future. We did rollout tuning. We initialized this guy here from that guy. Okay, so this is in some sense already like a fine-tuned version of the model, depending how you want to think about this. But this is basically for the maximized forecasting performance. And the reason, if you look at this, is really because there's like trade-offs in this. So you see like here, these are the different versions. Basically, if you pre-train with or without masking, but also you see like the difference between like the regular model and the rollout model. So if you look at the rollout model, you gain 14% in 6 hours forecasting performance. But if you actually already like randomize the forecasting lead time, you actually lose performance. So, if you just like want to have a fluent lead time where you sort of say, hey, I want to go like 24 hours ahead without auto regression. Okay, that's really important. Just like single shot suddenly, okay, 24 hours. I lose performance because, in this tuning, I really bake in the 6 hour time step, okay? And I can go to 24 by applying it 4 times, but I cannot go 24 single shot. But also relevant, like the reconstruction thing falls off the cliff. You lose like 43 or 60% reconstruction performance via the rollout tuning. Local and global is whether you're removing tokens or removing large areas, okay? Just to say, so here, not to go into too much detail here, but it's trying to say like what we found is there's sort of like a trade-off between like what you want to optimize for, whether reconstruction is something more relevant for you and, those use cases or forecasting, okay? All right. Then let's go back to the demo material, okay? So by now, not surprisingly, I said last time we checked in here, I said, there was like a minute left. You see now the validation code ran. Again, for those of you who are lucky enough to have enough GPU memory, you should be looking at the same thing. To everybody else, apologies, you should have gotten to this line here, okay? But you see exactly what we said before. Now we see, hey, inputs checked out, exactly. Validation checks out, again, I see in the first few hours, we're actually doing a bit better. Then things got a bit worse. At the end, we're doing better again. And overall, things are good. All right, we've seen enough here, okay? Let's actually look at an example. So for this, let's look at the director here, what we cloned earlier. There's an example director here. These are exactly the examples we looked at in the Git repo, okay? Make this actually a little bit larger here. There's exactly the same examples we saw like in the Git repo. So let's look at the Inference example first. Let me talk you through this here. Okay, so here we have obviously a bunch of random libraries we're importing. Same thing you would sort of expect. Hugging Face to get some data, etc. We're doing some seeding, not technically really necessary, the stuff here. We're checking that we have a CUDA device, fine. And now here, let's look at the configuration a bit. So here, we just give the model information. This is also in config files, so we tell like what are all the variables you need. Now, obviously, again, you don't want to change this like zero shot. It's going to be like a mess. But if you want to say, you want to change the variables, this is where you would start. Now, you see like the surface variables, static surface variables. This is like fraction ice, land cover, ocean cover, okay, elevation, I think, vertical variables, and then here the levels. No, we're doing a little bit of padding, actually negative padding. So because it's like the data is like 360 by 361, we're actually removing 1 pixel, I think, at the South Pole, maybe the North Pole, actually at the North, I think, okay. We're moving, I think, 1 pixel at the North Pole is kind of standard practice to go to like 360 by 576. So it's like nicer to like, divide this into windows, etc. In this case here, this is the zero-shot notebook. Okay, so you can like run this with different things. We run it with like 18 or with 6 hours. Let me change this to 60, for example. Okay. So different lead time, different input time, I said there's the 2 timestamps, and then we just give all the variable names. This is sort of a convenience object, this variable names thing. If you later on want to sort of like find what's the index of a variable, this is the order of the variables in the data set exactly. Okay, so this is kind of a convenience thing. The way the data set is going to generate data, they're going to be exactly this order. Okay, now here we download some data. This is going to run fast because we did this already with the validation script to download a lot of data. Okay, so that should be really like happening in no time. We download the climatology, as I said, it's separate data. And then the model uses a Fourier position encoding. If you look at the code, there's actually alternatives. Okay, but what we use for pre-training is the Fourier encoding. So you probably don't want to change this unless you actually want to like change the model again. Instantiate a data set. So the data set, obviously, this time it gets the time range, which is lead times. Time range is like data time you have data wave for, Then this is lead times, is a set of lead times. You could have multiple lead times, but then it's going to randomize them, You have similar, you could have multiple input times. This is the input delta. You say like, where's my surface data? Where's the vertical data? Typically the same directory, but sometimes not. Where's the climatology, surface and vertical? Then here you see where are static variables, where vertical variables, etc. Okay, so these are the names. So and then these are the names of the levels and the position encoding. Okay, so then let's look at the model itself. I told you earlier when I showed you like the loss function, I said we scale both the inputs and outputs. Okay, so what you see here is we need to download a few more assets. They're really small. This is the scaling of input and outputs. So as you surprise, mu sigma surface is a mean and standard deviation of the surface variables. Mean and standard deviation of the vertical variables, and anomaly variance is really, as it says, the variance of the difference from climatology that you have at the surface or in the vertical. Okay, so we can download all these things, then assemble them. You get a bunch of numbers. You can look at this here. If you look at the output sigma, this is basically the variances you need in there. It's actually interesting to note that if you look at the code, we clamp them. Some of those numbers are really, really, really small. I think if you look at the most highest vertical layer, the ice concentration is like the variance is 10 to the minus 34. So you see everywhere it says you 10 to the minus 7, we clamp this. Okay, we found training with like numbers as small as this is really a problem, especially since we divide by it. Okay, it leads to all sorts of issues. So we basically restrict the range of some of these variants for basic numerical reasons. Okay, and then here we say, all right, residual climate. This is again, the code is written. You don't have to do the delta from climatology. This is how the model was trained. Technically speaking, you could also do the delta from status quo, from persistence. Okay, this tendencies thing. You could also do the story where you just like give absolute quantities. So this is via this option. We set masking to 0. Now I said, because there was some confusion. We used to have like masking turned on in the notebooks, and then people would look at the results and say, hey, they don't look like super good, not being aware that the results were generated with like 90% of data missing. Okay, so we basically say there's no more masking right now in the model, but you can turn this on. You would not see it right now because the masking happens then early in the model, but you could then like, generate the output and look at it now. I'll show you some results of this later, but for now the masking, we just set it in the notebooks now to 0. And because the data is dense, we can turn basically the shifts in the models on and off. Okay, all right, fine. Now we just get the actual model weights. Okay, this might take a second, okay, to run. So you get the model weights from Hugging Face again. We instantiate the model. Again, if you're just doing inference, you probably don't want to change these things, but let me talk you through this a bit, okay? How many channels go in? Not surprisingly, okay, this is basically going to be this number of 160 times 2, I think, no? Basically 160 parameters with 2 timestamps. Then here, how many timestamps? This is the 2 timestamps that go in. How many static channels go in? Then here are the scalars, okay? All the scalars, scales the mean and standard deviation. There's an epsilon, which serves as a cutoff. Again, there's another mean, another standard deviation for the static data, and the epsilon is the cutoff. Output scalars, okay? There's nothing for the static data. We don't output the static data. Size of the image in pixels, you're generating. Obviously, in our case, this is, as I said, 360 by 576 pixel. You see here the patch size. So the patch size for the transformer. Technically speaking, you can change this without tuning the model. It's probably gonna be, you're probably gonna get artifacts from it. Okay, so the model's gonna run if you change the patch size. There's nothing in the model that really like, no, sorry, let me take this back. The patch size you cannot change. Sorry, that's the encoder. You cannot change the patches, but you can change the mask unit size. The mask unit size is the window size. You can mess with that, but it's gonna lead to probably some mild artifacts. But you can change that as a 0-shot thing, okay? Similar to the masking ratio. And there's a few more things here, embedding dimension, how many encoder decoder blocks, MRP multiplier, what you would see in these models, okay? So now that we ran this, it's actually really straightforward. Oh yeah, sorry, we import the weights, which we do now here. Sorry, this is gonna take a second, should have done this before. And then once we've done the weights here, we run an inference thing. It's really straightforward. Now you basically say, you get a data batch. There's a pre-processing function for the data. The pre-processing is really just sort of like assembling all the stuff I told you about. Now there's a lot of different inputs. It's actually interesting if you look at the batch object, there's a bunch of different keys. Now there's the actual input data, there is target data, which in this case we have in there because this is basically the training data loader. There's the static data, there's the lead time, there's the input time delta, and there's the climatology. Okay, so all this stuff is in there, and all the preprocessor does is basically shuffling the stuff around a bit between batches. It's not terribly complicated. The code is maybe a bit longer than it should be if you look at it. Okay. But this is what runs here. All right, I should have clicked on the load state dict here before because this does take a second. Yeah. And again, this is one of the notebooks. So this is again Inference with a full model where you are going to run into some memory issues. Okay, so the things that are sort of not affected by memory are the downscaling things we're going to do at the end, but these things are still affected a bit by memory. To actually see what this is running, you see the memory fluctuating here, at the bottom, which is obviously like, the weight's been first run to like CPU memory and then being moved to GPU. So you sort of see there's something going on here. If this is running too long, let me actually go to the next notebook otherwise, okay? So what you also see in here is, let me maybe start with this. I'll have to be a bit careful for memory reasons. So we're sitting on the same GPU. But let me start telling you about this rollout notebook, okay? So the rollout notebook is gonna look almost the same. What this does actually in addition is it then does also the forecasting stuff where you apply the model repeatedly to itself, okay? And there is some custom code we added here as a convenience thing, okay? But let me start talking you. Let's do this like this so we see what's going on, okay? Let me start talking you through this a bit and we sort of make use of the time together, okay? So here, again, it's a very, so let me say this, if you're following along again, both these notebooks are still like, somewhat memory hungry. Also, you don't want to run these at the same time, okay? That's why, so you see, I'm not actually executing this yet. I'm talking you through it, so we make use of the time. But I'm not going to start this yet. Okay, I'm going to wait till this is done. I'm going to kill the old notebook and then start the new one because otherwise it's definitely not going to happen from a memory point of view. So here, similar imports, torch, Hugging Face, what you would expect. Same thing as before. We define the surface variables, the vertical variables, etc. We get this convenience object with the variable names. Then here you see like now, lead time and input time. You saw these before, but now they're actually not lists anymore. They're single values. And remember I said this model just works in like deltas of 6, okay? So input time, you don't want to change this away from 6. The lead time is actually interesting. You take any multiple of 6 and the model is going to run it out until there, okay? We tested this until like 120 hours ahead, 5 days. I don't think I would run it much faster for reasons of, sort of questions of stability. But technically speaking, you can put something here, but it's going to at some point, fall apart. But we run this out for like 5 days. You simply put 120 here, the thing's going to run 5 days ahead. Okay. Let's quickly now here wrap up the old notebook. So here you said we run inference. Now we can plot some results already, and you see obviously now this is basically the model output. What you see like 10-meter wind speed, total column vapor, and 2-meter temperature. Here you see like now, when I say this convenience object variable names here, I say this is an index U10M. So basically you can grab them quite easily in this output data structure what the right index is, because this is like a fairly large tensor. So if you look at it, let's poke a bit around here together. If you look at what the model output is, out.shape, the batch index is 1, because we ran this in batch size 1, but then there's 160 output parameters, which are exactly in the structure I just mentioned. That's why we have this variable names object, latitudes, longitudes, effectively, okay? And let's look at this a bit together. Also, I said the batch object is somewhat complicated. If you look at the batch keys, I said, so the batch has lead time, input time, static, X, Y, climate. Okay, so X are the inputs. These are the 2 timestamps concatenated of the data. Y is a single timestamp target. Climate is the climatology. Okay, and you see all these are basically. This is not good. All these are basically tensors of comparable shape. All right. With that in mind, let's close this notebook down. While this is closed down, let's make sure our GPU memory is free. Yes, and let's go through the other one quickly. So I said before, let's just execute everything quickly. Lead times, input times, we don't lose data again, really trivial. Climatology, position encoding. We initialize the data loader. Note that the data loader is a little bit different here, okay? I'll tell you in a second why. Let me first keep executing these things so we don't wait again, while I'm talking. More download of the scalars, basically, and then we go all the way to the point where here, let's go that we execute the load state decline, okay? And again, this is only for the people really who have enough memory to run this. All right, so let me sort of talk you a little bit through this here again, what's going on. The data loader is different. Why is the data loader different? Because you need multiple climatologies. Okay, so you need for each time step and the autoregressive time step, we need also the climatology of the relevant time step, because the climatology does change, no? The climatology is different for each day and hour of the year. Obviously, it doesn't change year to year, but it changes, based on the day and the hour. That's why, the rollout data set actually it does all this assembly for you that it says, hey, even if you have only 2 timestamps input, you need all the climatologies of where you want to go, okay? Because they're part of the input. Technically speaking, also assembles some targets for you, because again, this is basically a training data set, but obviously you wouldn't necessarily need the targets, okay? Then the scalars are the same. Input output scalars, this is exactly the same story. You also see they come from the other repo here. The same story is now it's definitely we set the masking to 0, we set this encoder decoder shift to 0, etc. We got here the actual weights. Now we download the weights. Now we do in here is we actually instantiating the model, and we load the model weights, which actually we saw a second before. It takes a second, no? But here's basically a similar thing. This exact same model configuration. The difference is if you look at this, actually there's no difference. Okay, the model is instantiated the same way. There's some advanced options in here, by the way. We don't really need, you're not going to need this for any inference or so, but you see here, checkpoint encoder. So if you want to set base, you could use these things to run activation checkpointing if you're, fine-tuning, or training the thing from scratch, unlocking all the weights, no? So that's obviously quite key. I think when we pre-trained, initially we checkpointed every 3rd transformer block, okay? In the first phase of pre-training, we did the rollout training, we just checkpointed everything, okay? Was quite key. Then you get reasonable memory performance again with bfloat 16 and FSDP and stuff like that. All right. This is going to run for a second. Just again, we saw a second ago, it takes a minute to load the model to device. Once again, you can sort of follow along here and see what's happening with, main memory while this is running. And then let me show you this. So once this is run, it looks like almost the same code as before, except now you see we have the pre-processing function from the rollout loader. And we have a convenience script here called rollout iter, okay? It's actually kind of nice to look at. This is what this does is the following, this rollout iterator. See, it's just applied here at the end to the inference step, no? And if you sort of poke around a bit, if you want to, you don't have to, but the look at the actual code directory. If you look basically all this rollout thing does, it does multiple steps, how many steps you want to go ahead in the future. And it shuffles the input around, no? Because you always have to say the output of the previous model becomes a new input. So you see here, we run the model. And then here you basically say, oh, let's update the actual inputs, no? So you basically say, hey, we take the previous one and then we take the output, we combine those together, and this is then the new actually, input, etc. Okay. There's some shuffling around happens here. And this way, then the model sort of, does one step at a time via this convenience function. Okay. We are not done importing this, but we should be getting close at this stage. And then everything else going to happen is very prosaic. No, there's not going to be much to see. Basically, you run the rollout story, you get to a complete rollout, you plot everything, and you get results, okay? Let me actually at this stage, let's not wait for this to wrap up. I think you've sort of seen enough how to run this. No, you're going to get the same images again that we just saw. All right. So I think we've talked enough about basic inferences. Let's talk about like a use case. No, let's talk about the downscaling use case. Before we do this, let me show you one thing quickly. This is the following. I said the model can sort of like does this masking thing, so let me show you what this looks like. So you could, for example, like take total column vapor, remove like 3/4 of the data, what you see here, give this as input, and you get this as output, okay? Similarly, you can take like, and you see like, if you look at this carefully, you see like mild artifacts in here, from the Windows size basically, because they're being painted back in. But that's the point, removing like a lot of the data. You're moving very large regions are not there, and the model basically then starts filling these things, missing things in. Similarly, you can take wind speeds, remove like, 95% of the data. Obviously, this is kind of extreme, but then you sort of, get some reconstruction. Similar things to temperature. You can quantify this. You see like here, if you look at errors, obviously after like 80, 90%, this sort of really falls apart because we're not giving the model very much to work with, no? But effectively, you can quantify this, no? And see like, how good it performs. And actually, I think the numbers are in the paper for this, okay? All right. So let's talk about downscaling, okay? So downscaling, as we said, is for AI folks, maybe more like what you call super resolution, no? Is sort of here the story of how to increase resolution of the data. So what does it mean? Let me show you 2 examples here. One is, we did a very simple thing. We took the original data we had, the Mera data. We coarse-grained it like 6 by 6. We coarse-grained it 6 times. And then we sort of, brought the resolution back up. So what you see then is, just sort of very simply is, you say this is then the actual input, which is the coarse-grained data. This is the actual output of the model. You see the high resolution data it regenerates, and this is actually what the ground truth area is. Obviously, this is pretty pictures. You have to evaluate this, think about numbers, spectra, typically like power spectra you would plot, etc. But we're not talking about this so much in detail today. But then this is just obviously, the data we use for pre-training. Like, why would you care? We already have this data at high resolution. No, it doesn't really matter. So the next thing to do is then, let's say, hey, can we generalize this to like another data set? So what are we doing here? We took data from Codex, this is a high resolution climate downscaling story, okay? And we coarse-grained this like 12 times, and the difference now is, this is like obviously like a different story of resolutions. This basically goes now from, I think 150 kilometers is the coarse data to 12 kilometers then the target, okay? But also you see here, actually in this case, the model runs in a box. Okay, you sort of see this implicitly here. This is what we said, like the model, because it's comfortable with like all this masking and stuff missing, you can run the model in a box, no? Especially when you then fine tune it further, and also both of these downscaling use cases are sort of like 0 hours ahead use cases, okay? All right, so then the next thing here is what you see is, downscaling, 12 times downscaling of the sort of climate model data, okay? The architecture we use for these both cases is actually somewhat simple, but as I said, it's not just changing the head, because now we change in here, we change much more. Now we change not just the task, but we change the data set, we change the resolution, and we change the variables, and actually also the time step. And also in the Mera case, we kept the variables the same, but for the Codex case, we don't have the variables as for Mera. Also, we don't have the same time step. Codex comes at like 24-hour time interval, not at a 6-hour time interval, So that's what we said. It's good that the model is pre-trained in a way that is comfortable with like different time ranges. So because all these things change, we obviously need a new embedding for the models. Actually, what we do is like we take the coarse data, we train a new embedded layer, we do actually like some mild already upscaling before we hit the model. Then we hit the foundation model, the backbone. Then we sort of do some more convolutions, and then we do some upscaling, okay, at the end. And the idea is sort of roughly motivated by a bunch of things, you want to hit the foundation model roughly at the resolution that the model was pre-trained on, but also, if you look at sort of like state-of-the-art AI models for like downscaling or super resolution, and I mean like non-diffusion ones, just sort of transformer-based models or convolution-based models, often like a lot of the compute is in the coarse actually, is in the coarse area, okay? So just intuitively speaking, most compute, most like, layers are actually like operating on the coarse data in many downscaling models or super resolution models. This is sort of a similar pattern here, okay? We did a more complicated thing also, where, and I said, that's why it's not like one size fits all. where we basically say, all right, if we're looking at, numerical weather prediction data, we're looking here, for example, like, this is operational data from numerical weather forecasts. These are wind speeds. The question here is like, basically, can we go from like a 25 kilometer to a 2.5 kilometer resolution forecast, okay? And the architecture we used for this, sort of a bit different here, So again, we have two different weather forecasts, one 25 kilometer, 10 days ahead, one 2.5 kilometer, 2 days ahead. The question is like, can you get 2.5 kilometers beyond 2 days ahead by downscaling? No, and again, you have a change in resolution, change in data set, change in parameters. We improve the architecture actually here like a little bit, So we basically then say, all right, we have high resolution covariates, just obviously static stuff we know at high resolution. We have dynamic data at lower resolution and static data. And then we basically have sort of like a unit like stuff. And this looks like a unit, you might say, which in the way it is, but obviously like there is a lot of parameters down here, Like this little red box is a little red box, but this little red box is pretty heavy, So just to say this, but indeed the question is, otherwise, how do you view these different resolutions? You would use a unit. At the same time, how do you make use of it? You have like a nice pre-trained transformer. Well, you put it into your unit basically, okay? All right. And because these architectures are a bit complicated, and this is not trivial, actually, we sort of then use this TerraTorch library to wrap this, okay? So TerraTorch, is a library to assist with, inference and fine-tuning of geospatial AI models, not just weather and climate. Also, definitely was a big star of the show. I think the workshop we had like a week ago for the Earth observation models, okay? So let me show you then how this works in TerraTorch, okay? So if we head back here, yeah, by now our inference is here all done also, but let's back here. Let's shut down all of our notebooks. So we make sure we clean up memory again. If we head back here, let's make sure memory is free. Yep. Let's head one directory down. So based on our root directory, which for me is, I think, is a slightly different name than for you. Now that we're here, it's basically a simpler story of git clone TerraTorch, okay? Then let's go to the TerraTorch directory. Then we basically here make sure we check out the right thing. And then here effectively, yeah, in my case, I have to check out this commit. Okay, I think that by now this is updated in public. And then let's look here at the relevant notebooks. Okay, so the notebook is now in this repo here. There's lots of examples, okay? It's a rich library. There's examples, classification, segmentation, etc. But what here's like, there's a weather and climate tutorial for downscaling. That's the one we're looking at, okay? So here, the first thing we just sort out is, update the right libraries, as I said, because we're sort of doing two different things in the same environment now. And this is, by the way, as an example, not something where everybody can follow along. This doesn't have the same memory consumption issues, etc., that we had before, okay? Then as you see, is like Torch, actually, you see here, if you look at the imports, obviously it does various things like Hugging Face, you would expect it for Torch itself, but then TerraTorch actually also leverages Lightning, okay? For training, inference, etc., okay? So you're running Lightning here on top of this, just, help with these things. Everything else, like the sort of the things we saw before, okay? So let's do these imports here. Then you see there is a configuration file we need, which we get from Hugging Face. Now, obviously, from Hugging Face via the weather and climate downscaling Hugging Face, which is in Hugging Face as well. We also get some more data, this is very similar data to what we used before. This is just now the Mera2 data, okay? We're not doing run through this here, not for this Cortex data, but this is for this Mera2 data. Effectively here, I think this is all might have been cached already because we're basically doing the same thing as before, unless the directory is not quite synced because we're doing two different things here, okay? Like these notebooks are basically designed to be standalone. That's why sort of the paths might be quite the same linking up. Now we say for the config file, we say, hey, where do we put all this data? If you just execute everything, you can leave this all as it is. If your data were somewhere else, we could actually have put the paths here of the data we have. And you see like what comes in here is like similar to the scalars we had before, the anomaly variances we had before. Now, there's much more like configuration for the model because now we have the pre-trained foundation model plus, TerraTorch specific configuration, okay? So basically here for TerraTorch, we say, hey, we're going to use the backbone Prithvi, weather and climate as a backbone. We're going to use the decoder as a downscaler decoder, which means you're selecting this architecture here, okay? Then you say, hey, input channels, like how many channels actually are, we use as inputs. What's, how many timestamps? Now we just use one timestamp input, not two. Then you see like, what's the size of the data changed, static information. We change the scalars again, patch size, mask unit sizes, the window size, etc. Okay. Embedding dimension, now these parameters here, all stay the same because they basically like, define the backbone, but the other ones you can play with, okay? And if we just execute this, now we say we define a task as you would, okay, in the model factory. Now we can basically have a data module for downscaling. Okay, we see like similar patterns before, what's the time range? Where's the data located? Not much more happening here, okay? How many timestamps go in? How's the data being transformed? And then here, in this case, let's just run like an inference for this, okay? So basically, if you change this here, you can change this to setup train, and to setup trainer.train, you would start doing fine tuning here, okay? But for now, I think today, looking at time, everything, let's just run an inference here while this is happening. And I think we need to wait a second for the data set for the task to run here. All right, I'm looking at the Terratorch Slack chat. That's actually remarkably quiet. Not sure what chat we're actually using right now. But yeah, so we're waiting here, and right now, okay, we set up the task, which basically, starts the model. We create the data set now here. And then once this is done, we can now look also here at running an inference here, okay? So now you see like there's an inference starting here in a second. Let's see, everything surprising happens here. CUDA, TPUs, etc. Okay, yeah, so this is just an inference and should run fairly quickly. Good. Then basically we can grab the results here and not surprisingly, plot the results. Again, this is just inference, but basically see now the same models run here, but you see like the key parts about Terratorch to advertisers, not so much to be like plotted some pretty pictures, got inference. The key point is to say, it wraps more complex architectures. No, I mean, we said this here when I said like model arguments, I gave you like a sort of complicated list, and set up a task. But, we basically still use like, 2 node boxes here to configure like a more convoluted fine-tuning architecture, okay? The next thing is, if you want to tune this, it's basically, it piggybacks on Lightning to start custom tuning jobs on top of this, no? So this is also pretty straightforward. Now we just did this for inference, but basically trainer.train, with DM setup train would basically turn this to a training problem. And that's it, okay? So you see like we simplified a lot, generating something new from something old, even if we didn't do the full generation here. All right. I think then we're sort of coming slowly to the end of the story, okay? What you see here is like now, as I said, the Terratorch repo I discussed the various repos are in open source, okay? So I think we're actually doing a bit fast. We went a bit faster than I thought we would. Let's pause for a second and see, is there questions or comments? Again, I don't see any questions in the Terratorch Slack channel, but maybe there's something happening in the Zoom chat.
Okay, so Jan, thank you for your presentation. Well, it's it's amazing what you are doing. And no, there are no questions I see, but I have a question for you with respect to, I'm really interested in the downscaling.
Yep.
And I want to understand which is the limit in your opinion. So how many times we can downscale obtaining something which is enough good?
Yeah. So here, let me say this. It's an interesting point. So obviously, physics comes in scales, no? I mean, if you didn't teach the model about a certain scale at the physical effect of the physical scale, it's not gonna just know this out of nothing, no? So I think this is the limits. No, so I think here, what we're interested in is like, let's take a first step towards use cases like way beyond like forecasting, That's the one thing. The next thing is obviously you can definitely push this always a bit within the same scale, if you don't have like another effect, but basically if the model doesn't know about certain convective effects, you can push your floating point numbers as much as you want. It's not going to come in there, no? So long story short is, I think you can effectively downscale if you don't go to like effects the model hasn't seen. Here, actually, we pushed a bit beyond this, because we said that we trained on like half-degree resolution data and then downscaled to like 12 kilometers, which is like, less. But then we did this with fine-tuning. So the question is not so much like how far do you go, but how GPU efficient, how long do you have to tune the model? Okay, that's the question. So I'm not giving you like I'm not exactly answering your question. I'm not saying you're like, this is how far you can go. But I think so the boundary conditions are A, like how far do you want to push it? Like, do you cross the physical scale? And B, how long do you want to fine-tune it? That's really the question. No, because if you fine-tune long enough, you can learn anything. That's not really fine-tuning anymore. So in our case, with this version of the model, again, we got like reasonable results going to 12 kilometers, after like a day of fine-tuning, but reasonable results after like a day of fine-tuning, not saying like half an hour of fine-tuning and groundbreaking results,
Okay, so the limit you tried is these 12 kilometers with a lot of fine tuning. And so you recommend not to go down with respect to this one, or to be very cautious with respect to smaller.
Yeah, I mean, unless you sort of think that there's any reason that the model helps getting like, getting the large scale effects right, but at some point it doesn't matter anymore if you downscale from this to this. No, there's really like a question pushing toward like multi-scale models in the strict sense. Here we said the model should be multi-scalable. We basically the question we said then we pre-train on one scale and then tune to different scales, which works within reason, but within reason, because why would the model then go to entirely different scales? No.
Okay, thank you. And then I leave. I know that Rohini has also a question for you.
Thanks, Maria. That was incredible. It was quite rich, and we learned quite a lot. Quite impressive, I must say. You mentioned this here and there during the presentation as well. Could you help us understand what are the overall limitations of these models in general? Let's say I am a decision maker in one of the meteorological agency, and I would like to operationally use it to do the forecast or integrate it into our workflow.
It's a good point. I mean, this is like it's like a vastly evolving field right now. Okay, that's the thing. And also I think it really depends then, I think what you're discussing like, 2 months ago, 2 months later, there's really a gold rush. Now people basically realized if you take like 50 GPUs and point it at historical weather data, you'll find something useful. No, like the biggest breakthroughs have been definitely for forecasting. Okay, and definitely in this space. And then you have to think like what data unlocks this. So for example, the typical pattern has been like global forecasting on ERA5 data. That means you're landing in use cases where you say, 5-6 days ahead at quarter-degree resolution. It's not the same as like, high resolution, under-meter resolution forecast off the coast of Florida. And this has been partially not because maybe the architectures would be so different, but because people like the data is so available. The recipe was so clear. So I'm saying, so the first question is, are you doing forecasting? And at what scale? Then you basically, ECWF is operationalizing their own model, not in the sense that they give you like warnings for this, but the model runs every day AIFS now as an operational model. Now, so this has been operationalized. Let me say these models have some known issues for extreme events, because basically if you pre-train a deterministic model on root mean square error, it smoothens over extremes, which is also known. And people then, there's tricks around this. They run diffusion models, probabilistic models, ECWF, what is paper, CRPS, so there's tricks around this. But you see, if you just want to do like a global forecast, operationalizing is very clear. It's been done, And if you want to look at extremes, this is this. If you said you're interested in a high resolution forecast, I think the recipe is very clear. But then you might have to train it again and say, what data are we using? Are you using HRR? Some questions on boundary conditions, no? If you're looking like significantly beyond forecasting, okay, if you say like data assimilation, or downscaling, etc., there's the gold rush, again, it's not quite the same intense focus, no? And then there's probably a bit more work you have to do to put something really in operational practice, no? Which, again, that's one of the reasons we focus on these areas a bit, was because we said there is more to weather and climate and forecasting, even though it's the central thing, But there's also, it's less focused on and maybe less advanced. So there's a decision maker, let me say this sort of simply again, global forecasting, it's done, can do it tomorrow. Regional forecasting, you have to do some training, but it's straightforward. And then other use cases, I think there's lots of exciting things what can do, but we're a bit more in the research world right now than in the like, this is done world. And also when I said done, I didn't mean like done, there's lots of research left to do, but people are operationalizing these things to make decisions now and productize them.
Oh, that's great to hear. I think I have one quick question, one last question. You mentioned a little bit about the climatological aspect attributed to climate change as well. Could you elaborate a little bit more if I were to use this more for advocacy, using this model, also to help people understand what are the impacts of anthropogenic climate change itself?
So you say basically, you ask whether you can use this model to understand impacts, no? Is that what you're saying?
Yeah.
So I think, yeah, I think this touches on something I'm sort of interested in a bit, is like when, let me try to give an answer, okay? So, but most people do is like forecasting, no? And there was already a question people were asking, like, oh, can I trust the forecast? And obviously they evaluate them, then you trust it. No, but so when we first did the model, what some of our colleagues atmospheric physics did, they actually they poked the model, no, from a sort of physics point of view and said, oh, what if I change like the impact inputs, if I change, like, does the model respond correctly? You know, I put a bit more energy here, put some heat there, and how does the model behave? No? So suddenly you're saying, hey, what they're actually doing is they were actually like generating data whether it didn't happen, no? Because they were changing the initial conditions. Okay. And so an interesting question is, because you can run scenarios so quickly, technically speaking, you could say, well, let's put the GeoAI in this and generate synthetic events. Okay, that's a really interesting question. Also, in principle, there's like sort of this dream. We poked a bit around with this. Actually, I have this in my PowerPoint. You can take like a hurricane and then crank up the temperature by like a degree and see what happens. The tricky part is this. The tricky part is then obviously how far do you trust this, no? And not because you have the same question with the forecast. Do you trust the forecast? No, but the question is, let me say it slightly differently. If you start perturbing the initial conditions, is your perturbation physically consistent? You know, right now we took like an input signal that was consistent. When I say I take the thing and I crank up the temperature, you know, the model runs, it generates an output, and you think because it's a perturbation, it's probably all consistent. But you might have said, did I maybe take this off the manifold of consistent perturbations? So on the one hand, let me say, people often complain about this research saying, oh, it actually, like, you know, only like people in big AI companies can do it because it takes a lot of GPUs. And for me, it's almost the opposite. Like, you can run weather scenarios without an HPC cluster. Like, in this way, this like democratizes like meteorological research, no? This is actually really cool. Like, you get a single GPU, all right, we need the 30 gig memory, but you run an inference and you can generate like fake scenarios, no? But then there's a really nice research question. How do I know which inputs are correct? And then, sorry, to answer your long with your question, you know, but sorry to say this. If you say, hey, I take this model, I see how would Hurricane Milton if played out if the Caribbean sea surface temperature were 1 degree warmer? You know, how would like this happen out if I put some more energy in the atmosphere here? You know, so I think one thing that is a bit underexplored, and I think is really exciting. People, it's not like nobody's done this, no, but people really just focus on forecasting as like, what am I expecting to get? Not like, what could I have gotten if, you know? And if you think about it, if you can run inferences so cheaply and you can generate conditions so cheaply, and also again, the only question is like, you have to probably think about how to make sure that I'm making like a reasonable perturbation. But you could go to this notebook we said, capture the batch, go to the temperature, add a degree, and see what happens. And by the way, the paths obviously don't change. Also, you have to think what you expect. If you look at the hurricane paths, almost hit in the same area, you know. But then you see like wind speeds change a bit. So you see that we played a bit with this. I was thinking about showing it today, but then I was sort of saying, let's just keep it really simple. But yeah, it's a really good point. Thank you so much.
Oh, that's wonderful. I really feel like the future is here, and it's quite an exciting space to be combining AI and climate, and there's a lot of work that can be done. I see that we don't have any specific questions from the audience, and I would like to sincerely thank you, Johannes, for this great webinar. This workshop really opens up a lot of thinking and imagination for colleagues, including myself, to see how best we can move forward in the future with such powerful tools in our hands. And also big thank you to Romeo and Daniel as well, who assisted the participants behind the scene. I'm very grateful. And Maria, a big thanks to you for having moderated this event and for all your guidance throughout organizing these workshop series. Most of all, thank you for the participants for being here. I'm sure you learned a lot of new skills in the workshop. I sure did. And if you have any questions, we have the Slack channel, and please do keep your questions coming. All our workshop material is going to be available in the neural network. And of course, you can watch the recording on the YouTube as well. And I would also like to quickly remind everyone that we have another hands-on workshop planned for the 22nd of May, 2025. It's going to be on optimizing zero-shot segmentation of remote sensing imagery using LangORIS. And I am sure we will be able to organize quite many more in the future. Maria and Johan, very, very big thank you from all of us. Please stay tuned for all the exciting developments that is coming up. And once again, thank you, everyone. And I will give it back to Anna.
Thank you and bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.